Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're working examples solving for shear and bending moment diagrams in beams using the graphical method. In this example, we're looking at a simply supported beam with an overhang. We have a concentrated load and two different distributed loads on either side of the reaction at B. The lengths are given. We've also, to save some time, solved for the reactions, 2 kips at point A, 38 kips at point B. We've also extended lines down from each of the load discontinuities and created an axis for the shear force diagram, which we've labeled V in kips, and the bending moment diagram, which we've labeled M in kip feet. We'll start working the diagrams from left to right, starting with a shear force diagram. At the left end, we have a reaction force of 2 kips. That causes the shear to jump up by 2 kips. Over the first portion of the beam, there's no distributed load, so the shear is going to be constant, and we'll draw that as a straight line going across. Shear is positive in this region and equal to 2 kips. Then I reach the 10 kip concentrated force, which causes the shear diagram to jump down by 10 kips. So, and I'll go ahead and keep track of my calculations on the side. I have 2 minus 10 gives me a value of -8, so it jumps to -8. Then it's going to be constant again over the next region. And then when it reaches the distributed load, that's going to cause the shear to decrease linearly. Okay, and we can calculate the shear at point B by taking -8 minus the value of the distributed load, 5 times the length over which it acts, 2, which is -18. And I'm not going to quite draw this to scale since I'm running out of room, but it linearly decreases to a value of -18 at point B. Then I have the reaction force, 38 kips, which will cause the shear force diagram to jump up by 38. So we have -18 plus 38 is equal to 20. Again, the shear is going to decrease linearly over the right-hand portion of the beam due to the distributed load acting downward, and the value at the end we can calculate as 20 minus the value of the distributed load, 4, times the length over which it acts, which is 5, and the result is 0. And that's what I was hoping to see, because I know that my shear diagram should always return to 0 at the other end. So that's my sanity check on whether it's right or not. Now we'll work the moment diagram from left to right. Starting at point A, we know the moment at the left end is 0 because there is no concentrated force and no moment reaction at the location of the simple support. Then, because the shear is constant, the moment is going to be linear. Since the shear is positive, the moment is going to increase, so I'm going to draw that as a straight line. And the value at this point I can calculate as the value at the left end, which is 0, plus the area of the shear diagram. So let's do that. The area of the shear diagram is 2 times the length, 4, is equal to 8. So that's my value at this first location. Then, after that, the shear is negative and constant, so my moment is going to decrease linearly, something like that, at a higher slope. Okay, and I can calculate the value at this point as 8 minus the area of the shear diagram, which is 8 times 4, leads to a value of -24 at this location right here. So shear is positive, then negative. Over the next region, our shear becomes linear. It's still negative, so our moment is still going to continue to decrease, but now it's going to decrease quadratically. Okay, and as far as the slope, how I'm going to draw this is as the shear gets, as the value gets larger, my slope is going to get larger. So I'm going to draw it kind of curved in that direction, where the steeper slope is at the bottom. Again, I can calculate the value at this location by taking the value at this point minus the area of the shear diagram. That would be -24 minus, this is a trapezoidal area, so I'll take 1/2, or the average of the two values, 8 plus 18, and times the length over which it acts. That's 2 feet. And that equals -50. Okay? Last step over the right-hand overhang to the right of point B, my shear is positive, so my moment is going to increase. Shear is linear, moment is going to be quadratic, and it's sloping this way. Okay? I expect it to come back to 0. Let's check. -50 plus the area under the shear diagram, which is a triangle, 1/2 times 20 times 5, and that does indeed equal 0. So that's a check that it's correct. Finish it off, and it looks like that. I want to make sure that I indicate the value of all max and min and transition point. So I forgot to write in the 50 there. Everything looks good. Okay, that concludes this example.